Welcome to Lecture 2.1, Separation of Variables. We'll begin with an introduction. Now, first of all, the order of a differential equation is the highest derivative that appears. So this is something that we're going to use throughout the class. So for example, y prime equals 2y plus t. This is a first order differential equation, whereas y double prime equals 2y plus t. So that this is first order and this is second order. So if we have y, and we could have a mixed, so we could have y triple prime minus 2t to the fifth, y double prime equals sine of y, something like this. This is going to be a third order because we're just worried about the power of the highest derivative. So this entire section, section 2 we call it, not just this particular lecture, is about solving first order differential equations. And then later we will go on to second order. Okay, let's start with an example. Here's the simplest the simplest non-constant first order differential equation. The first one that we saw, this is exponential growth, assuming k is positive. Otherwise it's exponential decay, but either way we solve these the same way. So the first thing we're going to do is we're going to write out this equation in a slightly different form. dy dt equals, and we're assuming y is a function of t, is k times y. Now, the next step is something that you've probably wondered when you first saw derivatives in calculus, if you could do something like this. And yes, we are going to split up the fraction dy dt. You may have even asked your first year calculus teacher, can I break it? Is this a fraction? Can I break it up? And maybe they even said, no, you can't. But if they did, that's akin to your elementary school math teachers saying, no, you cannot subtract a bigger number from a smaller number. It doesn't work. Now, the truth is, yes, you can, but it's beyond the scope of the class. So let's do that, and we get dy equals ky dt. And now, what we want to do, the next step is going to be called separation of variables. I guess the whole process is, but here is where we're going to look at the dy and look at the dt, and we're going to put all the y's on the side of the dy and put all the t's on the other side. So we're going to write this as dy over y equals, well, there's no t, so our life is a little easier, kt dt. And this is called separate variables. And now we're going to integrate both sides. So let's put an integral here, and well, I'll put it here. I could put it outside the k, but I always like to pull constants out. Okay? So now, integrate both sides, we get the natural log of the absolute value of y, and we get kt plus c, a constant c. And remember, what we want to do is we want to solve for y. So we're almost there. Let's exponentiate both sides. Let's put an e on this side and an e on that side. And now, let's write this as, using the rules of exponents, e to the c times e to the kt. And now let's look at what we have. C is some arbitrary constant, right? So e to the c is some other arbitrary constant. So I'm going to just write this, I'm going to abuse notation and write this as c e to the kt. If you want to, you can use a different constant c than what I've used over here. I'm just going to pretend these are lowercase and that's capital. I'm just reusing the letter c. But this thing here, this is just y. So what we get is we get that y of t is c e to the kt. There is our general solution. And let's just check for a moment that this works. So I'll do that up here. Let's check. So what does it mean for this to be a solution? Well, that means this function satisfies this equation, which means if you take the derivative of this function, y prime, it's equal, you get the same thing as if you take the function and multiply by k. So does that happen? Take the derivative of this and we get k c e to the k t. This is y prime. And let's compare that to, so is that equal to k times y? Well, k times y is k times c e to the kt. Yes, indeed, those are equal. This checks out. So this is the general solution, and I haven't proven it, but I claim that all solutions to this equation are indeed of this form. Now, the astute listener may be scratching their head and thinking that I cheated along the lines here, and technically I did. So if you are wondering that, and even if you're not, I encourage you to, let's take a minute to explain why I cheated and why it really doesn't matter. So one suspicious step I did was, so c is any constant, right? And so e to the c is actually a positive constant. This can't be a negative number. So how did I go from a positive constant? I renamed it and I said, oh, this can be anything, this can be negative or 0 if we want to. How did I do that? Well, first of all, we verified that c can be negative. I mean, any value of c, this equation is the solution. This is going to work. So what did I do? Technically, yeah, I cheated when I did that, but it completely canceled with the fact that I cheated over here. So I said the natural log of the absolute value of y, then I applied e to that, and I claimed that I got y back. Well, yeah, I probably should have said plus or minus y there, right? Yeah, and if I had done that, I could reasonably justify that c can be any positive or negative number. Well, I haven't, I guess, accounted for the fact that it could be 0, but you can check that if c is 0, this definitely satisfies. So this separation of variables, it works. You can always, I have never in my life encountered a problem with separation of variables along these lines. When it's always fine when you get e to the natural log of negative y. Cancel that and just call that y, and say your constant and keep your constant. This little trickery, I've never seen it not work. So I'm perfectly fine with telling you that you can just do it like I did it. Okay, so let me ask a quick question. What is C? So let me put this up here. What is C? What does it represent? Well, the answer is let's write it as an answer. It's y of 0. So if you plug in 0 into this equation, you get c e to the 0, which is c times 1, which is c. So we call this an initial condition. And we'll look at this more later, especially in the next lecture. And in general, if I just give you a differential equation, you can find the general solution, which is a whole family of solutions. And then once I give you an initial condition, you can figure out what the constant is, and you can get what's called a particular solution that satisfies this initial condition. Okay, so more on this later. And this technique, of course, is called separation of variables. Let's do another example. This one is exponential decay, and it's really no different than the previous problem. The fact that there's a negative sign, that goes along for the ride with decay. But since we've just seen one of these, let's do this for extra practice. So we're going to write this as dy dt equals negative ky, and then we separate variables, and we write this as dy over y equals negative k dt, and then we integrate. I'm going to put the integral there because I can, and this is natural log of the absolute value of y equals negative k t plus c. Now I exponentiate both sides. And I'm going to do what I said I could do last time. I'm just going to write this as y and ignore the fact that there's the absolute value here, because those two fudge factors cancel each other out. So I'm going to say y is e to the negative, well, I'm going to write this before as c e to the negative kt. That's a shortcut you can always do. Just pretend to pull that constant down in front, and, well, I like to say this is lowercase c and that's uppercase c, and rename it. And so here's my solution. Wasn't that bad, right? Okay, now let's compare exponential growth to exponential decay. Exponential growth, of course, is y prime equals ky, and exponential decay is y prime equals negative ky. And both of these, I'm assuming k is positive. So let's graph the solutions. Exponential growth, the solutions are y of t, well, let's write them out first, equals c e to the kt. These are exponential functions that are exponentially growing. Here we have y of t equals c e to the negative kt. So for the first one, the solutions are going to look like, how do I want to do this? Let's draw it like this. So the solutions are going to look something like this. They will be increasing functions. Well, unless we're below the axis, in which case they'll be decreasing functions. And now remember that this value right here is our c. That's whatever our initial that's our initial condition. Let's write this as y of t. So choosing a different c, so choosing c determines where we start on the y-axis, and that is going to send us to a different curve. Think of this as exponential growth, like the value of your bank account. When you have $1 initially, that will grow without bound. But if you're $1 in debt, your debt will grow without bound as well. Now this is growth. Exponential decay is going to look similar, except these functions are going to be going toward 0. So this is t, this is y of t again. So this is growth, this is decay. And so here it doesn't matter where you start. You're gonna approach 0. You're never going to get there unless you actually start with 0 yourself. And then let me actually finish. Let me do one more problem, or one more example. What if, so I'll do it over here. What if k equals 0? So in other words, y prime equals 0 times k, or y prime equals 0. So this is actually a calculus problem. What functions have the property that their derivative is equal to 0? Those are, of course, constant functions. So we can, again, plot the solutions to these constant functions. So this solution here is just y of t equals c. And again, that's just a very basic first semester calculus problem. So if c is right here, we just go straight across like this. Now let me say one or two more things about this. So let's now picture that we have an equation like this, and k, and suppose we change the value of k. We're going to do more of this later, but let's suppose. So let me just ask an open-ended question. What about y prime equals ky for large k versus small k? So k in this case is approximately 0, and here k is much bigger than 0. What's going to be the difference? So the answer is, in the first case, think of it like your investment. It's going to grow quickly. Maybe I should even drawn it steeper than this. In your second case, your investment, if small k, is going to grow very small. Or small, it's going to grow not slowly. So picture taking an equation like this and changing the value of k. Make it large and then make it smaller and smaller. And these lines are going to get flatter and flatter. They're still exponential curves until k starts maybe at k equals 5, and then it goes down to k equals 1, and then it gets smaller and smaller. As it gets closer and closer to 0, these curves look flatter and flatter. And when it finally k hits 0, we get this situation. And then as k gets smaller and smaller, gets negative, these curves go from going upward to going downward, and we get a picture that looks like this. So it's a fun mental exercise, and we'll do more of this later, to think about k as like a tuning parameter that you can just maybe as a parameter that you can just move back and forth, and as you do it, picture how these solutions change. That's a fun exercise to picture how this thing changes, like graphically. Okay, so the last example that I want to do is something that we also saw in the first series of lectures, section 1. It's decay to a limiting value. It's essentially exponential decay. It's just instead of decaying to 0 like a quantity of uranium might, we're decaying to 72 degrees like the temperature of a cup of coffee might. So so we're actually going to see 4 different ways to solve this by the time we're done with section 2, and this is just going to be the first one. It's one of the, I don't think it's quite the easiest way, but it's the first one that we're going to learn naturally. So the first thing I'm going to do is a little bit of foresight. I'm going to write this as negative k y minus 72. Now I don't need to do this, but so why am I doing it? Well, it's much easier to integrate things or integrate something like y when there's no coefficient out in front of it, when it's monic. Otherwise, we have to do some sort of u substitution. And so we're going to get rid of that right away by pulling out that negative sign. Okay, so let's write this as dy. We didn't have to do that right away. We could have done it later, but I'm going to do it, get you in the habit of doing it first. So dy dt equals negative k y minus 72. And now we separate variables. Dy over y minus 72 equals negative k dt. And now we're going to integrate this. And we get natural log of y minus 72 equals negative kt plus c. And again, remember, if we had a constant in front of the y, like say maybe a 2 or a 1/2 or a negative 1, we would actually have to pull that constant out of the integral first before we can apply this integral law. Otherwise, we would have to do a u substitution. So I like to do that right away. And now I'm going to exponentiate both sides as before. Put an e here, put an e there. And I get that y minus 72 equals, and I'm going to write this as c e to the minus kt. Now I'm used to doing that all in one full swoop. And so this means that y of t equals 72 plus c e to the minus k t. So I'm going to circle that. That is my solution. And let me ask another question. I did the same thing earlier this lecture, but question, what is c in this case? And the answer is it's not actually. It's tempting to say it's temperature or y of 0, temperature of 0, but that's not the case. So the answer actually is So just plug in 0 and see what happens. Y of 0 equals 72 plus C. So it's not the initial temperature. This is the initial temperature. So this is initial temperature. So C is, what is C? C is the initial difference in temperature from the ambient temperature, 72. So it's like the I don't want to use variance, that's a statistics word. It's the difference. It's the, so C is the initial temp difference. Okay, so let's plot what these solutions look like. So this is 0. Let's say this is 72. Now, if your cup of coffee begins at 72 degrees, it's going to stay there forever. I should label my axes, T, and this is Y of T. And now if my coffee starts hot, it's going to decay toward that temperature, and no matter where I start, I get this decaying behavior toward the initial, or toward the ambient temperature. Okay? Now let me finish with let me bring back that idea from the last slide about what happens as we vary K. So what if K here is something about what K is. If K is large, like K is 100, then this exponential function is going to die out really quickly. Whereas K is small, this is going to die out a lot slower. So K directly determines how quickly our thing cooled off. So if we have, something like water might take a long time to cool off, whereas like a cup of coffee might go from 200 degrees to 72, or to close to room temp, and might take an hour or two. Whereas in contrast, if we have a pizza pan, a cookie sheet, it's metal, it'll do that in 3 minutes. So let's compare. Water might have a small K, and metal, like a metal pan or cookie sheet, is going to have a large K. Large K. So in this case, this goes to 0 slowly. Or not goes to 0, I should say goes to 72. How do I want to? Yeah, let's erase that. Goes to 72 slowly. That's supposed to be a 72, anyways. And this goes to 72 quickly. So imagine what happens, or mental exercise from before, is if this is, say this is the water, so this is a small K, and if we increase K, these curves are going to get steeper and steeper, and this whole set of solutions is going to get steeper and steeper, and the solutions are going to approach the ambient temperature quicker.